In order to understand chemical reactions, we need to be able to understand bonding, and for that we need to be able to predict molecular shapes based on Lewis structures. In that regard, the valence shell electron pair repulsion model is used. So the VSEPR model, therefore, this model, or the valence shell electron pair repulsion model, is based on minimization of repulsions between electron pairs. We are talking about minimization of repulsions between a bonding pair and a bonding pair, a bonding pair and a non-bonding pair, and repulsions between non-bonding pairs. Let's take different electronic cases, beginning with a 2-electron pair case. And in this case, we take beryllium chloride, BeCl2. The first step would always be drawing a Lewis structure. In order to be able to draw a Lewis structure, we need to calculate the total number of valence electrons in the compound. For beryllium, the number of valence electrons is 2, and for chlorine it is 7 from each of them, and there are 2 of them. The total number of valence electrons in this case is actually 16. So 16 valence electrons total. To draw a Lewis structure, we draw the central atom, so it's beryllium, and the surrounding atoms, chlorine here and chlorine on the other side. All right, and then we draw a bond between beryllium and each of these chlorine atoms. That's like step number 2. Next step would be to satisfy the octet on surrounding atoms. So now chlorine has 2, so 3, 4, 5, 6, 7, 8, and here also this chlorine is now surrounded by 8 electrons, satisfying the octet rule. All right, now if we count the number of valence electrons used so far in this structure, we would find it's 8 on this side and 8 on this side, and this adds up to 16. And this is good because we have 16 valence electrons available. The electron pairs used are actually also 8, so 3 non-bonding pairs, 1 bonding pair, so 4 from each of these chlorine atoms, which add up to 8 electron pairs total. And so this is reasonable. If you look at the structure of beryllium chloride, you would find out that it is linear. The overall arrangement of electron pairs around beryllium, in this case, or the orbital shape, is linear, and the molecular structure is also linear. So let's write that down. So the electronic arrangement or arrangement of electron pairs or orbital shape is linear. The molecular shape is also linear. Because of this linear molecular shape around beryllium, in beryllium chloride, the bond angle is 180 degrees. So this is actually 180 degrees because the molecular shape is linear. We can actually construct a model using Darling models for beryllium chloride to achieve something like that. So this is the central beryllium atom, and these are the 2 chlorine atoms. You can see that the molecular shape is linear, and of course the bond angle is 180 degrees.